venue aujourd'hui. En fait, je peux parler un peu de français grâce à Thierry, en fait. Titi qui est ici, à Clermont-Ferrand. Thierry, c'était son nom à Paris, dans le laboratoire de Claude Jopard. On a passé une année ensemble là. Et il m'apprend toute la langue, mais ça fait... mais ça fait 20 ans, mais j'ai perdu pratiquement toute la langue, donc il faut que je donne une présentation en anglais. Okay, I won't torture you anymore with my terrible French. Thanks for being here today. This is my first time coming to Clermont-Ferrand, and I'm really excited. It's such a beautiful, I've never been here before, and it's beautiful. You have a church made of basalt. That's really cool. And I put this talk together just this week with some new papers that have just come out last week and will be coming out in the next couple of months. So hopefully it's all mostly new information. I want to do something a little bit different today, talking about mantle oxygen fugacity. We know a lot and have a good global understanding from basalts, mid-ocean ridge basalts, which we have samples of from all over the globe. But not since 1990, not for 30 years, has anyone paid attention to abyssal peridotite, which are the residue of melting. You know, from the continents, for example, we have a xenolith record, and we get a good view of the oxygen fugacity profile in the continents from xenoliths. In the oceans, we have no xenoliths. So we have no sense of the redox profile in the convecting upper mantle and the convecting mantle beneath the oceans. Presumably, the mantle has some oxygen fugacity. It's solid, it ascends. It starts to melt. At the moment of that melting, the basalt, is in equilibrium with the residue, the peridotite. Then they separate, and they go separate ways, and they're not constrained to be in equilibrium anymore. So they could be telling the same story originally and different stories now. So we're going to look at peridotites today. We'll still talk about basalts a little bit, but a lot about peridotites. Okay, so normally I would spend some time telling you how important oxygen fugacity is, but we're all petrologists and geochemists. We all know that oxygen fugacity of the mantle sets our world up to be a habitable world. It's the oxygen fugacity of magmas that allows volcanoes to emit carbon dioxide and water, life-giving compounds as opposed to, say, carbon monoxide or hydrogen gas. In addition, this is a photo from the Aleutians, and it is a place where we think new continents are being generated. And continental rocks have higher oxygen fugacities. The rocks record higher oxygen fugacities. So having the oxygen fugacity that the mantle does really defines our planet. You know, from a bird's eye view, we have a blue planet with ocean basins and continents, and a lot of this is due to oxygen fugacity. And I just wanted to say, because just interrupt anytime, shout out any questions, don't hesitate to jump in, because if I'm speaking too quickly or anything like that. Okay. People have recognized for a long time the importance of oxygen fugacity in the oceans, and this is the seminal work in the 1980s, 1986, of Christie, Carmichael, and Langmuir, who used the oxidation state of iron as a proxy for oxygen fugacity. And then in 2005, this is the work of Bezos and Humler. Both of these are wet chemical studies, titration studies of iron in basalts. And the idea was that they would see a really nice correlation between magnesium oxide, MgO, and 3+ to total. The idea is that 3+ iron, ferric iron, is incompatible in olivine. So as olivine fractionates from the basalt, the 3+ content, you can see the prediction would rise. But actually, if you remove this one point, there's essentially no trend at all. And then Bezos and Humler saw essentially no trend, and even saw some places individual ridge segments. You know, you see these kind of crazy crazy shapes. So not the systematics that people were expecting. And again, this is wet chemistry titration, where you chip off the glass and you get some minerals in there and you dissolve it in acid and get the 3+ total. If we look instead at just the glass with X-ray absorption near-edge structure spectroscopy, we can look at the 3+ total ratio just of the glass only, no minerals. These are a bunch of Zane's spectra, and the spectra shift smoothly from very, very oxidized spectra to reduced spectra. And this region here is the pre-edge region. And in my work, you can parameterize these spectra all different ways. In my group, we look at the centroid, which is the area-weighted average of this pre-edge energy. And we use that as a proxy for the oxidation state of iron in these glasses. And so with the calibration, is based on room temperature Mossbauer spectroscopy. These are all experiments on basalts conducted at 1 atmosphere. We measure the centroid with Zane's, and we have the 3+ total ratio from room temperature Mossbauer spectroscopy. So that's the calibration. And the main finding that I think is gaining more widespread support, and I'll show you some new data, is that the spectra of natural mid-ocean ridge basalts, there's one here in red that I'm showing with these background subtracted spectra, is that most basalts fall somewhere between the quartz phaelite magnetite buffer, QFM, -0.5 and +0.5. So the spectra of the glass is the spectra of experiments that have equilibrated at the QFM buffer, independent of what the 3+ total ratio is. The spectra look like the QFM buffer. Now, as I said, this was done with room temperature Mossbauer spectroscopy. And we just had a paper come out last week. This is working with Mark Hirschman and Honglo Zhang doing cryogenic Mossbauer spectroscopy. So Mossbauer spectroscopy at 10 Kelvin and looking at temperature series. So taking Mossbauer spectroscopy at many temperatures from 10 Kelvin up to 300 Kelvin or so. We expect from the mineral, this is a literature compilation of mineral data, that the recoilless fraction in Mossbauer spectroscopy, and these technical details don't matter too much, but I'll just mention that we expect 2+ iron and 3+ iron in minerals to have different recoilless fractions, which corrects the room temperature Mossbauer measurements. Most people had dismissed this in glasses because comparisons of a single cryogenic spectra to a room temperature spectra didn't have the precision to resolve the differences. But doing careful work like this across a temperature series with a helium dewar and nice cold temperatures, we could resolve a very small correction, a factor of C of 1.1, which only leads to a 1 or 2% difference in the ferric-ferrous ratio of the basalts. But this correction explains quite a bit. If we look at the 3+ total we measure with Zane's and compare that to the 3+ total we predict using Kress-and-Carmichael's relationship between the oxygen fugacity of the furnace and the 3+ total ratio of the glass as a function of composition, we always knew that the room temperature Mossbauer measurements fell slightly above the 1-to-1 line. That's a dotted line here. And now the Zhang et al., with this slight correction, gives essentially perfect agreement between, this is a wet chemical study, titration study, of Kress-and-Carmichael and the Mossbauer work, once we consider recoilless fraction. So this is new Mossbauer work. Looking with that precision, because Zane's is much more precise than wet chemistry, I'm showing here some representative error bars. I didn't put them everywhere, just for clarity, but you see some on the black symbols here. The black are some new data. we're now looking at global mid-ocean ridge basalts. And when you look with the precision of Zanes, we have a much nicer correlation between MgO and 3+ to total that people predicted would be there, again, because ferric iron is incompatible in olivine. So as basalts crystallize, it acts as an incompatible element and increases in its concentration. And the other thing is we get really nice on at single segments, like here the Cane fracture zone in the oceans is a place really known for really nice liquid lines of descent, really systematic behavior in those basalts. And we see they follow essentially this olivine fractionation trend. This is a model trend, these green squares, of olivine fractionating. And the slope of the global data, the individual data from the Cane fracture zone are indistinguishable from the model trend. So with that, we can now take into account low pressure effects. If we're trying to understand the mantle, we have to make sure that we know if we're analyzing rocks that are very primitive or more evolved and take that into account.
But sorry,
yeah,
the ferric iron behavior is not controlled by olivine, is it?
I think during low pressure crystal fractionation, I think it is controlled mainly by olivine. You're pulling olivine out. The olivine takes only 2+ iron, and the 3+ iron builds up in the liquid. So there's about a 3% difference in the ferric.
So this is a fractional crystallization?
Fractional crystallization.
Okay.
And it's really, I think you're bringing up a really good point. We don't see this kind of clear incompatible behavior during mantle melting. We don't see a correlation between, for example, sodium corrected for low pressure fractionation. We don't see correlations between sodium and ferric iron. So I think the story during mantle melting is a different story that we don't understand, and that's something that's kind of the point of my talk. I agree with you completely. But the low pressure fractional crystallization, the ferric iron is behaving incompatibly due to olivine.
So here we are looking at the evolution of the magma.
Yeah.
In the
crust. Yeah.
In the crust.
Yeah, exactly. Not melting, but crystallization. But when we sample basalts, we have to know where we are in order to look through back to the mantle, because we want to be as close to this end as possible. It's a great point.
You are basically saying that all the titration study included some micro oxide or something.
Yeah, I mean, the precision overall is a little bit lower.
Yeah.
They definitely contain some microphenocrysts.
Okay.
In fact, in the paper we're about to look at in a moment, Hugh O'Neill thinks that there's also an effect of sulfur in the natural samples, because we have this really great agreement between the Mossbauer work and the Zanes work in experiments. We don't have great agreement on natural rocks. So you have phenocrysts, you have sulfur. That Hugh O'Neill hasn't put out any data, but when you talk to him, that's what he says. So there's probably some data to suggest that that's true. I just haven't seen it yet. That's right. So the average 3+ to total ratio of all this global system with the new calibration is 14, and that's QFM minus a couple tenths of a log unit. If you use Kress and Carmichael to convert this number to oxygen fugacity. And when we did this originally in 2011, it was 16. So it came down a couple of percent. That's due to this recoilless fraction, this new cryogenic Mossbauer work. Okay. So I'm going to take a very brief digression, because this paper came out last week also, the same time as the Zhang paper. And if you're really interested in redox, and you're probably not, but if you are, you would see that these two papers, the Zhang paper and the Berry paper, are very different in their interpretation of Mossbauer spectra. So this is a figure from that paper. Obviously he didn't have the paper, our paper, which would shift these from 16 to 14. the Christie et al. Study, Bezos and Humler, these are now Morb basalts. And these are 42, so this is like 100, 100, 100 glasses, 42 basalts from Berry, and they get a mean of 10%. Okay? Also by Zanes, also with Mossbauer spectroscopy as the baseline. So they've put forward a very different, a very new interpretation of Mossbauer spectra. But for the point...
From the same location?
It's global. It's a global compilation. 42 basalts. Some are the same. Some are the same. These 3 studies, actually all 4 of these studies have some samples that we've all measured. But in fact, there's a lot in common between this study and this study because all their samples are from Smithsonian. So it's all, their 42 are a subset of the 100. And they get, this difference is not location. It's, they're interpreting the Mossbauer spectra very differently than our group or groups previously. It's a
southern hemisphere effect. It's a southern hemisphere effect.
Yeah. Okay. So that's different, but for the interestingly, there's still broad agreement because both of these studies agree with going back to 1978, looking at magnetite-ilmenite pairs in Morb, that these are both at QFM. Now I know that won't make sense because how can 10% be QFM and 14% be QFM? What Berry et al. Are recognizing are that the spectra, the Zane spectra of the glasses, look like the spectra of Morb at QFM. So what they're saying is that Kress and Carmichael, the relationship between FO2 and 3+ to total is wrong. They throw it out. Shit. Kress and Carmichael. So that's how this is QFM, but 10%. Is that they're doing away with Kress and Carmichael. I'll talk about it a little more. I don't know if I'm not sure that that's right, but the good news is that there's broad agreement between these studies that the Mantle's at about QFM, upper Mantle.
But QFM is kind of virtual because what you're basically doing is you're driving your glass, your basal to QFM because you're removing the olivine. But that doesn't mean the mantle is QFM.
Yeah, that's right. You have to. That's exactly my point here. Is you have to correct for this. You have to correct for this, and when you do, you project back to near
it's equivalent,
QFM.
but it doesn't.
It's not too far.
But
yes.
When you correct for fractionation, you correct for olivine fractionation. What about the other phases?
Well, this
Is
is
that 6%
empirical.
MGO?
It's empirical. I'm not correcting for olivine fractionation. I correct on the slope of the data.
So you don't
So,
assume
I don't
partition
assume a partition coefficient. I don't assume a
But if-
slope. I'm just saying that the slope of olivine is statistically the same as the slope of the data.
And what would that give? What would that give you for a partition coefficient for iron 3+? What's the value that it would give you?
Well, this olivine fractionation assumes that 3+ iron is perfectly incompatible in olivine. This is very simple. And like I said, it's just the slope of this is the slope of the data within error, but I'm not making any interpretation about that. I would correct, these data from Kane on that slope, empirical.
And then also, it's just teasing, but maybe then when you reach the QFM, you don't crystallize olivine anymore. So.
Oh, come on.
Yeah, I think you do. This is so QFM. This is QFM in here. So the bulk of the data are. Well, we'll get into that. We'll get into that now. Well, exactly. That's why I'm looking at the peridotites, at the residues. Right? We have the melts, but we also have the residues, and that's the whole point of my talk. So we'll press on. Okay. So these data now. I want to say. I'm now going to. This is. Being revised right now for EPSL. This is the work of Suzanne Berner. She's my graduate student. So smart, wonderful, and I give her all the credit in the world for putting these data together. So I just want to shout out to Suzanne. This is the same plot we were just looking at, flipped on its side. Christie, Bezos, the Zhang study, and Berry I put in just as a line because they don't have, because they no Crescent Carmichael, they can't convert the 3+ to total ratios into QFM. They can't make this plot on QFM because no Crescent Carmichael. So they just say that the spectra are at QFM. Okay.
Why don't you compare with like AP and ferric ferrous ratio?
It's important. It's important when we're trying to look at the mantle below the surface.
Okay.
We need to use experiments, Natalie's experiments, and models. Okay, and those we have to use oxygen fugacity, not ferric ferrous ratio. Also, the ferric ferrous ratio is a product of pressure, temperature, and composition. The whole purpose of the Crescent Carmichael relationship is it takes a ferric ferrous ratio and considers the composition to get you to QFM. Okay, so if we want to compare peridotites to glasses, we have to do it in oxygen fugacity space, not iron oxidation state space. So these data have bothered me for 10 years. This is the seminal work of Brinzia and Wood. They published 35 abyssal peridotite oxygen fugacities using spinel oxybarometry. It's the equilibrium between spinel, orthopyroxene, and olivine. When you have those three phases, they constrain the oxygen fugacity. Two things: huge range compared to the basalts, and shifted to lower oxygen fugacity. The residues are at lower oxygen fugacity than what we think from Zane's. So this is troubling. Is this a different story? Is it the same story? What is the process going from the peridotites to the basalts that leads to this offset? And also, why is this range so big? So we're going back to look at these abyssal peridotites, of which, again, there have only been 35 for the globe ever published, and no one's looked at this in 35 years. We just talked about this, the relationship between looking at the peridotites now. We have these phases in equilibrium, and we can calculate the oxygen fugacity from that. Okay, so we care both about the diversity of mid-ocean ridge basalts and the diversity of peridotites, because we want to understand what's the possible range of oxygen fugacity in the ocean basins. Is it the same everywhere, or do we have regional variations? And what's the absolute value of oxygen fugacity? Is the mantle actually down at QFM -1, or is it at QFM? Because that log unit of difference makes a difference to, for example, the depth of melting. This is an experiment done by Rajdeep Dasgupta and Mark Hirschman, published in their Nature paper in 2010, and then they have this model in 2013. And the only point I want to make here is that the depth of melting on the wet peridotite is 100 kilometers more shallow than the carbonated solidus, okay? But melting the carbonated solidus requires that the mantle be fairly well oxidized. You need a very oxidized mantle because the graphite carbonate transition is oxygen fugacity dependent. So this is where the real importance of oxygen fugacity comes through. As we're interpreting low velocity zones, electrical conductivity, where metal saturation occurs in the mantle is all going to be a function of oxygen fugacity. So we need to know the absolute value of oxygen fugacity to have our experiments and models, to be able to interpret our experiments and models to understand our geophysical signatures about the initiation of melting, electrical conductivity, all like that. So our open questions are, is the mantle oxidized enough to explain the geophysical observations with carbonated melting? And what is the oxygen fugacity profile of the upper mantle? We have a good sense from the continents, from xenoliths, but again, in the oceans we have no xenoliths. So how do we get that depth profile? This is just to remind you, a study of Stagno et al. 2010 and 2013. They're showing different isoplaths for the ferric ferrous ratio of the bulk mantle. showing that you initiate carbonated melting once you're oxidized enough to hit the graphite to carbonate transition. And which of these you follow, we don't know, because we don't know this for the oceanic mantle. We have a better sense for the continental mantle. The big point I want to make is that these lines don't connect to the Morb source. If we look at the silicate melt and model it, it would plummet down. We don't know how to connect, exactly as you said, Muriel, we don't know how to connect the residue, solid residue, to the basalts we see at the surface. We don't have the models to do that. We don't know the partition coefficients. We haven't done the experiments to know the effect of melting and how 3+ iron behaves during melting. Okay, so looking at the peridotite, what are our problems? Well, one of our problems is that none of these 35 sample locations matches any of the 200 basalt sample locations. So one possibility is that this is a sampling bias, just a systematic bias due to a low number of samples in the peridotites. A second problem we have is that these are two different techniques. The oxybarometry is completely independent of Zane's and Mossbauer. It's thermodynamics based on electron microprobe measurements of these phases, whereas Zane's, we're looking at the glass. It's a spectroscopic technique. It's based in Mossbauer wet chem. And we've never compared these head to head. So now I'm going to tell you about a study that we've done looking at these two techniques on the same samples. So we've done a suite of experiments at 1 atmosphere with known oxygen fugacity, because we can set the furnace to exactly the oxygen fugacity we want. And we've equilibrated silicate liquid, basalt, with OPX, spinel, and olivine. Then we can do Zane's on the glass to get the 3+ to total ratio of the glass. And we can analyze the solid phases to do spinel oxybarometry and get an FO2 from that directly. Same sample, know it's in equilibrium, good. And we are, I don't know if we're happy, we are glad to know that the two agree. Okay, so when we use Zane's and we get the 3+ to total ratio, and we take that 3+ to total ratio, we use Kress and Carmichael and get the furnace oxygen fugacity back. Here, we take the spinel oxygen barometer, spinel, OPX, olivine, we get an oxygen fugacity, and this is the 1-to-1 line in black, and then the gray is the regression. There's no offset. You know, they pretty much lie on the 1-to-1 line. So this eliminates a big, one of our big problems, which was that we thought maybe these two techniques are offset. From our data, it seems that they agree. So good, we can move forward. Problem 3, the study of Brinsian wood was done in 1990. So 30 years of new data and new mineral models have happened in that time. And the Brinsian wood study was done with the Nell wood model for magnetite activity, for the activity of magnetite and spinel. And the Nell wood model doesn't include titanium, which will affect the stoichiometry in the spinels. And it also is not calibrated at high spinel chrome number. So it starts very parallel to the Sacking-Giorso model, but because it's not calibrated, it kind of blows up at high chrome number, at the same chrome numbers where we have natural spinels. So here's just a data set from Tonga. These are Tonga forks. It doesn't matter what they are. There's some peridotites. And you can see the data reduced with the Nell wood model or the Sacking-Giorso model, looking at the oxygen fugacity recorded by the peridotite versus spinel chrome number. And you see different dependencies. The previous thing that I showed you, this where we get the furnace FO2, uses the new Sacking-Giorso model. That's the model that's used in melts, for example, if you're familiar with melts. It reproduces the experiments better than using the Nell wood model. So using the Sacking-Giorso model, we'll now go back to the Brinsian wood data and take a closer look. The first thing we see with the Brinsian wood data is of these 35 samples, only the ones in green from these fracture zones have olivine, orthopyroxene, and spinel. 11 of the samples. The rest, they made up the compositions, not made up, but they guessed, estimated the compositions. So we only have 11 with the required phase assemblage. There's a few, this orange one, for example, from St. Paul's Rocks, Brinsian wood eliminated that because it's not at a spreading ridge, right? It's kind of a weird location in the Atlantic Ocean. If we eliminate the samples that are not, that are off-axis at ridges, and we only look at samples at ridges and only at samples with the phase assemblage that we need, we have 11. And when we apply the Sack-and-Ghiorso model, rather than the Nell-Wood model for spinel activity, we get a slight increase in oxygen fugacity of about 0.3 of a log unit. Okay, so that closes the gap with the basalts a little bit, but it certainly doesn't put them together. It's just a slight adjustment using more modern data. The fourth problem we considered is the problem of low temperature seawater alteration. This is what in class textbook you say, peridotite, it looks like this. But when you take a rock from the ocean floor, it looks like this, okay? Very highly serpentinized. And the question is, what is the effect of all that serpentinization on the oxygen fugacity of the phases, low temperature alteration? So this was a study that was done in the Tonga Forearc. The beautiful thing about the Tonga Forearc is you get the entire range of alteration from perfectly fresh, they look like xenoliths, all the way to completely serpentinized. And what we see in these dredges, like this orange dredge here, we have peridotites going from fairly fresh to highly altered, and we don't get any big trend in oxygen fugacity one way or the other. One dredge is giving one answer. So at least in the natural data, we don't see that, once you get very altered, it all goes to hell. No, we don't see that. It stays fairly constant across the entire range.
Don't you need the temperature to do this?
That's the point. The temperature is locked in at the time the peridotite, at the closure temperature of the peridotite in the mantle.
No,
The temperature of seawater alteration has not moved the FO2 of the rocks. Yeah.
If you do a thermometry, you get about 800 degrees.
Yes, and I'm going to show you that in a minute. Yes, so that's right. You get 9. In fact, our sample is 900 degrees. Yes, from the ridge. That's what we're going to look at now. So here's our, as I was saying, here's our global coverage of basalts with redox measurements. Zanes, wet chemistry, they're all over the globe. Here are the, here's the coverage of peridotites, just here. And very, very much fewer, and none in the same location. So the study I'm going to show you to present the results from is high-density sampling along the southwest Indian Ridge. The southwest Indian Ridge is a beautiful place on the planet because that's one of the only places, there's only 2 places we know of where peridotites and basalts are both exposed at the seafloor. This is the ridge axis. The green are peridotite locations, and the black are basalt dredge locations. We even have some dredges where in one dredge you get peridotite and basalt. This is pretty rare in the ocean, and we looked at 31 basalts and 41 peridotites. So you already see we have analyzed more peridotites on this little stretch of ridge than the entire previous global data set because we're trying to compare basalts and peridotites and look for systematics in the melting and see if the basalts and peridotites agree in one location. And we were completely surprised by what we found.
Just a question.
Yes.
Is that peridotite or aspergite, or is that the residue?
Lertzolites and Harzbergites. As long, you must have OPX, olivine, and spinel. So you might have CPX or not, but once you go to dunite and you lose the OPX, you can't use the oxybarometer anymore because there's nothing to fix the
you want to
silicate
make the
activity.
equilibrium between both phases.
This is what we found. Tights from across that one segment, the oblique segment of the Southwest Indian Ridge. Yes, Ken, 900 degrees and 0.6 GPa, that's what the thermometry and the barometry are telling us was the closure temperature and pressure when diffusion, major element diffusion stopped in these rocks. What's astonishing is that as we look along this segment across longitude, we get 2 orders of magnitude in oxygen fugacity in one dredge. On the thin section scale, we have one value. It's homogeneous on the thin section scale. You take a thin section, the spinels everywhere all agree and give one FO2 within the uncertainty, within the precision of the measurement. But within a single dredge at one location, we get 2 orders of magnitude. And
Excuse me, what do you mean by a single dredge? It's a one sample or a bunch of samples?
throw the bucket over the side of the ship,
Plenty of samples.
different samples.
Okay.
So that peridotite, this peridotite,
Okay.
are they the same from the same place? Who knows? It's down at the bottom of the ocean. You don't see it. You've been to sea, right? So it's like, you don't know. Just from this location, one basket haul of the ship.
Yeah, but still, they know the distance, like sometimes 500 meters.
Yeah,
something.
yeah.
It's not that
It's the
fast.
scale of, right? It's less than a kilometer, probably.
It's not the
right?
same formation.
Yeah, but not the same. You might be dredging up a slope
Yeah.
from many depths, for example. It's hard to say. I haven't put any lithological information on here about Harzburgite, Lützolite like that, okay? What I'm saying is we get the entire previously reported global range in peridotites in one location on the Southwest Indian Ridge, and that really surprised us. We thought we would get one number all the way across, but instead we got this huge diversity, very close locations, giving very different answers. Yeah?
When you get such variations in a single dredge, does it correspond to large variations in mineral compositions for the spinel or MG number and silicate?
Yes, that is what we're looking at very hard right now. So the first thing that we're publishing is just the variation. We give all the mineralogy, all the compositions. There's no clear offset, say, between Lützolites and Harzburgites. We don't see any clear trends. There is a slight tendency in this data set to see that at higher chrome numbers you get more reduced oxygen fugacities, but there's not enough data across a wide enough range to really know for sure. But that was the point of this. We didn't know what we would see when we went into this data set. But no, there's no clear, obvious, oh yes, this is the process that leads to this heterogeneity. So we're left to wonder, is this real heterogeneity in the mantle on the kilometer scale that's being homogenized by basalts? Or, as Ken pointed out, these are not the temperatures and pressures at which basalts and peridotites are in equilibrium. This is the temperature and pressure where the peridotite decompressed and cooled and finally stopped major element diffusion. So we have to compare it to the basalt, we have to project back to mantle conditions, and that's what we'll do next. Right, I just wanted to show that our range from Southwest Indian Ridge is as big as the range from the global system, but offset higher in oxygen fugacity. You'll see in a minute that that's just because we're using these closure temperatures, and Brindisian would assume a different temperature and pressure. We'll show that in a minute. And to say that the basalts, now we're surprised that when we initially processed the data, it's the peridotites giving more oxidized values than the basalts. But again, that's because of temperature and pressure, as we'll see in a moment, and other reactions that happen subsolidus. So exactly as you're saying, we have in the source peridotite and basalt together. They're in equilibrium. They love each other. Then the basalt follows an adiabat. straight to the surface, rises buoyantly along an adiabat, and it is recording, most basalts record around 1 GPa, around 1200 degrees. That's they're shooting up from the mantle, and all you have to worry about is how the QFM buffer moves with pressure and temperature for melts, and that's well known. We know from Kress and Carmichael, we know how basalts move relative to QFM as a function of pressure and temperature. The peridotite follows some geotherm, okay? It doesn't follow an adiabat. So they diverge. The peridotite, if we now look along this geotherm and we plot the buffers, QFM, along this geotherm in oxygen fugacity, the peridotite, as it cools and decompresses, records higher and higher oxygen fugacities because it is moving on a different path than the buffers, okay, along the solidus. So we can look at that now. This is temperature and pressure, so I'm moving along the geotherm, okay, from hot and deep to cooler and shallow. And remember, we equilibrated all the way over here at 900 degrees and 0.6 GPa. If we don't change the composition, and we only change the pressure and temperature, have isocompositional decompression and cooling only, the peridotites will record higher and higher oxygen fugacities due to pressure temperature conditions only. But there's also exchange reactions. So there's a great paper by Voigt and van der Hunt from 2011 where they look at how spinel chemistry changes during this cooling and decompression process. There's an exchange between orthopyroxene and spinel of ferric iron and aluminum. These exchange reactions occur on a slightly different slope. You can't even tell on this scale. But if we take into account those exchange reactions, we'll also lead to cooling and decompression recording higher and higher oxygen fugacities. The final thing we have to consider are modal changes. As you cool and decompress, spinel will grow at the expense of olivine and orthopyroxene. So as pressure and temperature decrease, more and more spinel is growing, olivine and orthopyroxene becoming less. If you don't change the ferric-ferrous ratio of the phases, and that's a huge assumption, we don't know, right? We have no information to say one way or another. The ferric iron will become diluted in the spinel, and oxygen fugacity goes down slightly because of diluting the ferric iron in more and more modal spinel. So we don't know what's going on. We don't have enough experiments. We don't have good enough models to know if peridotites follow this trend or something in between. There's about half of a log unit of uncertainty in what this cooling and decompression will do to the peridotites. We want to know what the peridotites' FO2 was before they melted, right? We don't have the data and models to do that yet. We have about a half log unit, at least, uncertainty in how to project to higher pressures and temperatures. So this uncertainty is going to lead to about at least a half, I'd say, well, we've just said, let's pick the middle between here and here. We think the actual truth is somewhere between these two extremes. But there's going to be some inaccuracy of about a half a log unit that we can't resolve right now. We don't have good enough models. But it doesn't affect our precision. Okay? This will shift our entire data set by a half log unit one way or the other, but we don't think it will lead to changes in the relative positions of the peridotites unless there are, we think all the peridotites come up because we get them on the surface. So they all got colder and came to lower pressure. So choosing that halfway point and now correcting the basalts and the peridotites to when they were last in equilibrium. If we do thermometry on the basalts and the peridotites to model the chemistry back until the time they're in equilibrium, its temperature is more like 1320 and 1.25 GPa. We think those are the pressures and temperatures when the basalt at the southwest Indian Ridge, for that geotherm, which has had so much work done on it. We have really good models for the geotherm there and for the Mantle flow regime. Projecting back to those conditions, the basalts are at about QFM, and the periddotites have this huge dynamic range all around the basalts. What does it mean? I'm not 100% sure. Does it mean that the mantle is heterogeneous on the scale of kilometers in terms of oxygen fugacity, and that the process of melting and generating basalts homogenizes and averages? That's what we see in isotopes. That's what we see in trace elements. We know that that's true for isotopes and trace elements. But oxygen fugacity is not an isotope, right? It's a thermodynamic parameter. You don't mix them.
You calculate it from the composition, don't you?
Yeah, they're calculated for the compositions, yes. So yes, that's a possible interpretation, is that this heterogeneity is real. Another possibility is that there's some systematics, as you asked, there's some systematics during melt extraction, okay, that varying degrees of melt extraction or processes happening after melt extraction generate heterogeneity in the oxygen fugacity recorded by periddotites that is not present before they melt. We don't know. So those are two possible interpretations. But the baseline conclusion of this work, this study that we've done, is that by quadrupling the number of measurements on periddotites, we're starting to learn a lot more. And so I think it's a great time in earth science to go back and revisit some of these older seminal papers like Brinzian wood. Microprobes operate much faster now than they did in 1990. We have more spectrometers, and we can get a lot more data to hear more about the FO2. Now, I'm going to return to our overlying questions and ask, if the mantle's at QFM, the basalts would indicate, yes?
On the last slide,
yes.
Even though the FO2 looks similar,
yes,
the Fe3 plus contents are completely different from the periodotite and the basalts.
Yeah.
So having
but that doesn't matter.
Having heterogeneity is not completely surprising, because then if you recycle the basalt, then you create a completely material with completely different Fe3 plus.
That's right. The 3 plus doesn't matter. You have to convert it to oxygen.
But if you put this 3 plus from the basalt into another new periodotite, then the fugacity will shift completely.
Yes, I agree with that completely. So I think that at some level, the offset between the Brinzian wood periddotites and the basalt is just a sample bias. Their samples are from over here. The question is, how heterogeneous is mantle oxygen fugacity on a global scale for the periddotites? Is this dynamic range present everywhere? Are there regions that are more reduced and others that are more oxidized? And would we see that in our geophysical observations? I agree completely. The 3 plus to total iron only gives you one proxy to calculate oxygen fugacity. You can use vanadium scandium is another proxy. The spinel oxybarometry is another proxy. Magnetite-ilmenite pairs. Petrologists love making proxies for oxygen fugacity. So we have many to try, and sometimes they agree and sometimes they don't. That's why we need experiments in the lab to compare these proxies directly, head to head, so that we know when we have measurement bias between different methods. Okay, so I want to finish up this talk with just a short little vignette about the heterogeneity that we see in basalts in mid-ocean ridges, because this relates to this bigger question of this talk. When we're trying to relate experiments and models and geophysical observations to the petrology, we have data in geophysics for the entire globe, and we have point samples for basalts and periddotites. So what can we say about these values? And I'm going to go to a different place, also in the Indian Ocean. I love the Indian Ocean right now. This is the Australian Antarctic Discordance. This is an area south of Australia. This is the Indian Ocean and the Pacific Ocean. And this region, south of Australia, the AAD, is a region of chaotic topography. The ridge is all broken up. The topography goes up and down. It's like a jumble there. There's a very famous geochemical boundary at this location. This was first published in Nature by Klein and Langmuir in 1988. As you travel from the Indian to the Pacific side along the ridge axis, you have a discontinuity or a discordance in the geochemistry. A sudden drop in strontium isotopes, sudden increase in neodymium isotopes, lead. You see it in everything. Trace elements. Every isotopic system shows a shift as you go from the Indian side to the Pacific side across this topography. Now, the other thing you see is a difference in major elements. Sodium contents are lower on the Indian side, indicating lower potential temperatures. The crust there, geophysically, the crust is much thinner on the Indian side than on the Pacific side. Klein and Langmuir, without geophysical data, looked at the crustal, just without tomography, looked at the crustal thickness and the sodium, and their thought was that there was a convective downwelling here, right here, and that convective downwelling was separating the Pacific mantle from the Indian mantle, which has, geochemists will call it like the Dupal anomaly, Dupal isotopic signatures, and that this convective cell came together here, separating the two. We now know from very large tomographic experiments that something different is going on. This is the study now of Ritzwaller et al., JGR in 2003, where they did a tomographic study. Here's the discordance in the topography on the ridge, and we're now looking west into the Indian Ocean as a function of depth. This is a tomographic image, and we're looking at the color coding is the shear velocity perturbation. And what they've imaged is this giant blue, this giant seismically fast fossil slab. They interpret this, the Australian Antarctic mantle anomaly. It's a giant, long slab lodged in the mantle at this location. So yes, it is cold, 100 degrees colder mantle temperatures on the Indian side than on the Pacific side. It's colder. The slab is neutrally buoyant. It's cold, but it's had basalt extracted. So the iron contents, Ritzwaller suggests that the iron contents must be lower because because of the gravity measurements. This is neutrally buoyant in the mantle. So it's geochemically light, but it's cold, and there's no convective downwelling. This is a big slab stuck in the mantle at depth. So looking at the same basalt, we measured, using Zane's, 77 basalts, high density sampling. So looking at up to a dozen basalts from each dredge, each of the 11 dredges in the original Klein and Langmuir study, going across the AAD from the Indian side, I'll put those all in pink, and the Pacific side in blue. And so just to summarize, the Indian side is colder, has lower, that should be, I can't believe you're recording this, should be higher sodium, colder, isotopically enriched, and trace element enriched. You have it, I just have to cover this up now. Barium and potassium, higher barium potassium ratios. And we did redox across that. Again, we were surprised by what we saw. Again, the Indian side's in pink, the Pacific side's in blue. The first thing we see is that all this new data continues this kind of global trend between 3+ iron getting higher as you fractionate the basalt. But in every location, very generally, I'm sure you can see with your eye without me doing any averaging, I don't need to do any math for you to see that on average, the Indian side has lower 3+ to total ratios than the Pacific side. The blue points are all, on average, much higher than the pink points, higher 3+ to total ratios. when we convert, but I said the compositions, the basalt compositions are different on either side, so we have to convert these values to oxygen fugacity. We use Kress and Carmichael to do that. When we do that, though, the results are very striking. Whether you're looking at 3+ to total, these are the segment averages, are the circles, and the every individual basalt are the crosses. We convert that to FO2. We see this large discontinuity, just like the isotopes, just like the trace elements, in redox across this boundary. The difference in the average oxygen fugacity of these two sites is very statistically significant at the 99.99% confidence level. We know that these are different redox. The difference far exceeds the error bars that we have on any of the measurements. And so there's a redox discordance as well. What does it mean? We know that the Indian Ocean is famous for being geochemically different. There's many ideas for what could make it different, going back to Zindler and Hart in '86. Is it delaminated subcontinental lithospheric mantle? Is it subducted crust? Metasomatized mantle? I mean, they have many ideas for what this Dupal mantle is in the Indian, but the Indian Ocean seems to have been isolated from the broader global circulation for potentially billions of years. And what we're showing here is that it seems like the Indian Ocean is also a reduced end member globally. Does this mean that we have hemispheric differences in redox, where the Indian Ocean as an entire basin is more reduced than the Pacific and Atlantic? I don't know. I only have the data across the AAD. I don't want to speculate too much, but all these samples have geochemical signatures that are like the Indian Ocean. The other thing that's, I think, really important for our understanding of process that comes out of this study is that this side is the colder side because of that slab. Less melting, less melt, colder temperatures. And the only paper that's come out recently that tries to relate mantle potential temperature to redox is a paper by Glenn Gaetani, came out in 2016, looking at the relationship between ferric-ferrous ratios during melting and potential temperature. And he predicted that the temperature dependence would be that colder mantle would be more oxidized. So the exact opposite. We're finding the exact opposite. So if Glenn's model is correct, that means that the actual difference in redox is actually much bigger. This is like the minimum difference. Or maybe this model is wrong. I don't know which, but it's certainly not consistent with this model. It doesn't explain this offset. And the only other thing I'm just going to close with is that we had seen previously some relationships between 3+ to total and lead, or QFM and lead, or QFM and strontium ratios when we look globally. But now when I go back and look at that data set, these samples on the reduced end with the really extreme isotopes are the Indian Ocean. So is this a trend, or is it just the rest of the world and the Indian? I don't know. I don't have enough data. Or is this a smooth variation that's telling us something about recycling processes globally? I think the jury's out. We don't know, but these are the data we have now. So that's it. Thank you.
Merci beaucoup. Est-ce qu'il y a des questions? Maybe I didn't get something. You said the Indian Ocean is, since Hart and Zindler, a lot of recycled material? Supposedly.
Yeah, I'm not an expert, yeah.
So, so it means, but it is at the most reduced one. So it would mean that recycling is reducing the amount?
I have no idea.
Which is, I mean, to me, counterintuitive.
Yeah, I agree. No, for me too, believe me, I'm 100% with you on that. They have the Dupal anomaly, maybe it's other models that are delaminated continental roots that have continental signature. We know that continental roots, we know diamonds, for example, come from continental roots. A lot of the literature suggests that continental roots are very reduced, more reduced than the same depths in the ocean. So maybe that would explain it, how you could have a continental-like isotopes, but reduced conditions. But I'm just speculating.
Okay,
I
if
agree
it's
with you.
continental crust, then yeah.
Yeah, continental.
I get it.
But if you look at continental weathering, if you look at sediments, terrigenous sediments are very oxidized in the oceans. If you look at terrigenous, what's weathering off the continents, as you can imagine, up here in the air, things get really oxidized. So it wouldn't be continental sediments, but maybe it's continental roots. I don't know. I think we don't know.
What do you know about the Verilites and Websterites?
In terms of redox?
Yes.
Nothing. We in our group have not, there's no, we have, in the continents, the xenolith record goes quite deep. There are continental xenoliths going down hundreds of kilometers, and the lithology changes, and they become more and more reduced, going deeper and deeper. So we think we know that the mantle becomes deeper in the continents, at least. We have evidence for that. We don't have any whirlites and websterites in the oceans, so we have no data. What do you know about whirlites and websterites?
I wonder. Probably nothing.
No, but those peridotite from Southwest Indian Ridge, they have those peroxenite bands, you know? That's
Yep, they have peroxenite veining. So that's another thing that we're looking at. The abyssal peridotites have veins running through them. Some of them have had melt infiltration with pervasive plagioclase. We now have, we are starting to look at those. The first pass, we were trying to look at samples that didn't have pervasive melt infiltration, right? Because we're trying to get back to the mantle. But in terms of looking at process, I think you're right. We have to look at the veining. Again, to look at the FO2 recorded in the veins, we still need olivine, pyroxene, and spinel, right? But starting to look at peridotites that have more and less alteration, more or less metasomatism, more or less melt addition, plagioclase, are all things we can do to start to look at the process, look at variations in chrome number, look at different lithologies. So I think we're just kind of at the tip of the iceberg. There's not too many places on Earth, though, where you can find both basalts and peridotites together.
I have a question on your trend for the basalt FO2 as a function of olivine fractionation.
Mm-hmm.
Do you think, I'm thinking about the extremes.
Yeah.
Do you think that if you reduce the degree of partial melting, you may go much further? Are you interested by this part, or
Yeah.
do you think it can be a hand limit? And on the other side, it depends also what's the pressure, or where the melt occurs, and how far can you go in both
Yes.
directions? And
Yes. Can I use this on this
Sure.
board? We're looking here all at crystal fractionation.
there should be an end on both sides somewhere.
Yeah. So if you look at sodium 8, I'm going to actually put that on this axis because that's how people are used to looking at it. Sodium is very well known to increase with differentiation. And all the, probably Charlie Langmuir's biggest contribution to petrology is looking at these relationships and saying, okay, if we want to compare a crystal fractionation trend like this to one like this to one like this, and we want to compare different places on the planet at a single fractionation extent, and Klein and Langmuir and Planck and Langmuir, they use 8 weight % MgO to correct back So we're looking here and here, each one, right? Sodium behaves incompatibly during fractionation. We have a similar situation here. So with every single one of these basalts, we can correct along a slope. Sometimes we just have one basalt from one ridge. Sometimes, like the Cane Fracture Zone or the Southwest Indian Ridge, the oblique segment, we have lots of basalt, and we can do a real correction. And we can calculate sodium-8 for each location and calculate iron oxidation state at 8 weight % MgO for each location. Everyone would predict that 3+ iron is behaving incompatibly during mantle melting. And the bulk Ds that have been put forward are about 0.1 for the bulk D for a typical mantle assemblage. So that would lead to a relationship like this. We don't see that anywhere. The data of Bezos and Humler and our data, and I don't have it in this presentation, but we can look at it afterwards, I have it on my computer, is a broad field of negative or no correlation. Different segments show no correlation. Globally, there's a slight negative correlation or a big blob. So either 3+ iron is less incompatible than we imagined, perhaps because spinel holds a lot of it back. The xenolith studies would suggest that it's incompatible. This is definitely a place where we need a lot of experiments now to understand why we don't see, this is, a bulk D of 0.01. We don't see that. The trends we see in individual places show either no correlation or grossly a negative correlation. So there's a great plot of this in the Cottrell and Kelly 2011 paper, or Bezos and Humler 2005 show this lack of correlation. I think that we don't understand ferric iron during melting. Yeah,
Excuse me, isn't this just based on the assumption that you're just melting electrolytes?
Nephlite?
Electrolyte.
Oh,
Peridotite.
Lursolite. Okay.
Yeah. That there is no pyrophonite
Yes,
contribution.
absolutely. This is a peridotite assumption. Once you have peroxenite, exactly, you have lots of phases to store. So I think that petrologists, if you survey petrologists, that's a place where there's a lot of disagreement. How much peroxenite is in the mantle, right? You have people saying that there's lots of peroxenite in the mantle, and others saying that there's almost none, or others saying that the systematics are controlled by peridotite, even if there's peroxenite. And what is the role, for example, when we measure these, when we have some of these peridotites that are Hartsbergites that are so depleted that they might be coming around again in the mantle flow and not even contributing any melt to the basalt anymore, but we still sample them and measure their oxygen fugacity. I think there's a lot that we don't know. But yes, this assumes Lurtzlite, and peroxenite would really change the story. I agree.
Par contre, là, du coup, on va devoir arrêter les questions parce qu'en fait, il faut qu'on libère la salle de séminaire. Donc, pour ceux qui voudraient continuer à discuter avec Cottrell, ça serait du coup en dehors. Je suis désolée.